Okay, folks, what I'm going to do is give you a very quick tour of this CD segment of the PowerPoint. What I'm going to do is emphasize the points that I want you to know for the test. Because this is being presented at the very last minute in the term, I'm only going to emphasize rather simple qualitative things that I'd like you to retain. This material does pick up in a way on all the stuff we've done about transition dipole moments. Having done that, you ought to be able to understand it. But it's too late to expect you to really wallow in the details. So what I'm going to expect you to remember are the bullet points, which are shown to the left over here on the screen. So I'll read those. And then anything else that I expect you to remember, I'm going to circle in red. And there'll be 1 to 2 sort of factoids per slide that I'm going to ask you to remember. Okay, so circular dichroism spectroscopy is a tool for approximate quantification of protein secondary structure. Now I'm going to go through the bullet points, and these I think are fair game to ask you questions about on the test. Again, there will be nothing technical or deep, no calculations, no critical thinking, but a solid memory of the most basic points in this presentation, which I will again explicitly highlight for you here. So circular dichroism measures small differences in absorption between of left versus right circularly polarized light. So what that's all about, if you don't understand it already, is explained in the next slide. Because right and left circularly polarized light are mirror images of one another, only chiral molecules exhibit CD. Again, that's something I would expect you to remember, that to have CD, you have to be, for a molecule to have CD, it has to be chiral. It is dependent primarily on the chiral spatial arrangement or environment of light-absorbing chemical groups. So to have CD, you have to absorb light. To absorb light, as we'll talk about in a few minutes, you need to have a change in dipole moment and going from the ground state to the excited state. The things that we look at in CD are amide bonds. Most applications are looking at amide bonds. That's what's shown over here, which I'll talk about in a moment. But you can also look at amino acid side chains and nucleotide bases. They absorb light, and they are they at least have chiral arrangements in the polymers where they exist. The most common application is approximate quantification of protein backbone conformation and secondary structure. That's the application shown over here. In this application, the protein backbone amide bond, the backbone means the amide bond. These amide bond spectra are modeled as a linear combination of basis spectra corresponding to reference secondary structures. That's explained in a slide later on. The secondary structure estimates are approximate, both because of physical limitations. All secondary structure elements don't give absolutely consistent kind of spectral signals. But then also, this is a very noisy technique, and that's another thing I'm going to expect you to know about. And one of the slides later on explains briefly why. And so finally, and then there are a couple technical points in here. Most of them I'm not going to expect you to remember this year or know about. But this one is sort of so high level that I would. Reasonable accuracy in secondary structure estimation can only be achieved if accurate data are obtained at 195 nanometer. That's down here. Sorry, the pen is a little bit funky. That's down here. Most solutions are rather opaque in that, meaning they don't barely let any light through at all in that wavelength range, which makes it hard to measure small differences in absorption between right and left circularly polarized light. And so it's technically challenging to get good data down here, but such data are needed to quantify secondary structure. So what I expect you to remember from this slide are these bullet points, and then one more thing. If you look at this scale, it says arbitrary. And this is all that I could find on. This is the most illustrative thing that I could find online easily. If I were making a proper textbook out of this, I would dig through data from the lab and do something proper here, or even do a little experiment to do this properly. This is an arbitrary scale. That's basically a sin in CD. This CD is what's important in CD is the shape. I'll say more about that in a moment, the shape of the curve, but also the absolute magnitude of the curve. And if you don't put it on the right scale, that absolute magnitude is uninterpretable. And so this is on the website of someone who is prominent in the CD field. And it is, again, I would say sinful because it is not on the absolute scale, and therefore it's actually really hard to interpret it properly. I assume they're all on a consistent relative scale, but if they're not on the absolute scale, you can't really do the curve fitting. You can't estimate secondary structure. So the only thing on this slide I would expect you to remember, other than the bullet points are the fact that the absolute scale is important, but these data here are not really plotted on the proper absolute scale. Okay, so what is shown here then are 4 different protein structures. Most of them have alpha helical, significant alpha helical content, A, B, C, and only one has only a small amount of alpha helix, that's D. This happens to be a gastric enzyme called chymotrypsin. If you look down at these CD spectra, you'll see they all have pretty similar shapes. There are variations in them, but the only one that is very different is the blue one, which is D, which is chymotrypsin. The rest of them all have a similar shape, and that shape is dominated by the signal from the alpha helix. And if you look at the almost entirely helical, the predominantly helical protein C, myoglobin, an oxygen carrier, you will see it has a characteristic peak at about 197 or so, and then double minima at around 208 and 222. That is the characteristic shape for an alpha helical spectrum, and also the reason that all these things that have helix sort of look a lot like the helical spectrum is because the magnitude of the signal from the helix is much stronger than from any other secondary structure, and so alpha helices tend to dominate CD spectra, and therefore your ability to quantify helical content is much better than that of other kinds of secondary structure. And however, even helical content cannot be quantified well unless you measure the peak reasonably accurately at about 197, and you put it on the proper absolute scale, which these people did not. Okay, the next slide just explains briefly what left and right-handedly circularized polarized light are. There's only one thing I expect you to, well, let's say 2 things that I expect you to know here. Well, actually, one of them is covered on the next slide, so I'd say just one thing I would expect you to know here. That is illustrated in the top row in this diagram, and this is trying to show that linearly polarized light is an equal superposition of right and left-handed circularly polarized light. And so the rest of this is sort of interesting. You can read it, but the only thing I expect you to know from this slide is that linearly polarized light is a sum of equal amplitudes or magnitudes of right and left circularly polarized light. It's also worth noting that if you have unequal magnitudes, which is what happens if there's different absorption, if you send let's say a linearly polarized light beam through a sample that absorbs right and left differently, the linearly polarized beam is an equal superposition of right and left. If right is absorbed more than left, or vice versa, what emerges is an elliptically polarized beam, and that's why CD is measured in ellipticity. So that factoid, I guess I do also expect you to remember, that differential absorption of right and left circularly polarized light gives elliptical light, and CD is measured in ellipticity, which is sort of a weird unit. I'll comment on that briefly later on. But all I will ask you to remember is that it's measured in ellipticity because you get elliptical polarization if you have unequal absorbance of right and left circularly polarized light if you start with a linearly polarized light beam. Okay, so that's all of that. So here, I think there are only 2 things I want you to take home from this slide. So what is shown here is this would effectively be a map of the electric field vector in space, assuming this was the direction. So this is a sort of a 2D projection of what's supposed to be a 3D graph. What's graphed here, this is the direction of propagation of the light, and this is supposed to show the electric field vector curving around that direction of propagation. So this is helical. If you freeze the light, if you could freeze the light beam in an instant or measure its electric field along this spatial axis at one moment in time, what you would see is that the directional electric field would spin in a helical fashion around the direction of propagation, and the helix would have one-handedness or direction for left circularly polarized light and the other for right circularly polarized light. The only thing I want you to take away from this is that left and right circularly polarized light are mirror images of one another, and therefore, if you have a molecule that's a mirror image of, sorry, it's bad drawing. If you have a molecule, if you have 2 molecules that are mirror images of one another, they will interact identically with right and left circularly polarized light, right? Because if the right circularly polarized light, sorry, this looks like a mess, but hopefully you can get the point. The right circularly polarized light is the mirror image of the left. If a molecule is a mirror image of itself, it will interact the same way with both of these polarizations of light. So that comes to the take-home message here, which is this on this slide again. One of the two factors I want you to know. Actually, this one I think this is really probably the only very important one, which is that an achiral molecule is its own mirror image, so symmetry requires an achiral molecule to interact equivalently with right and left circularly polarized light because they're also mirror images of another, and that means that chirality is a minimal requirement for optical activity, which is another way of saying differential interaction with light with alternative circular polarization. So to have CD, you have to be chiral. If you're achiral, you can't have CD, because if you're achiral, you are the mirror image of yourself, and therefore you necessarily, physically, by symmetry, must interact equally with right and left circularly polarized light. I wouldn't test you, I don't think, on what's over to the right here, but it's important for knowing what's shown in the next slide, which is important. Actually, this is fairly simple, and so there is, I guess, maybe a second factoid here that's worth knowing. The amide in CD spectroscopy, to determine secondary structure, you look at the differential absorption of the amide bond. The amide bond, of course, has partial double bond character. Amide bonds absorb roughly between 190 and 240 nanometers. The molecular orbital description, simple molecular orbital description of this delocalized bond, right? There's a double bond, formally a double bond from C to O in the amide bond, but because there's a lone pair on the end, this has partial double bond character, and this then is so-called delocalized. What's called delocalized in a classical chemical treatment, valence chemical treatment, ends up producing molecular orbitals, quantized molecular orbitals of the kind showing down here. Effectively, the sigma bonds here are not shown at all. What this is showing are the pi bonds. The pi bonds end up having two occupied orbitals. There's a pi orbital with a positive phase at each of the three atoms. These are supposed to represent the electron clouds on the O, the C, and the N. There's one with a positive charge, positive phase on on the O, let's say, and negative phase on the N, and then some positive phase, spherically symmetrical positive phase around the middle C. And then there's another one that goes O positive, C negative, N positive again. So these are the three molecular orbitals, and of course the electrons occupy the molecular orbitals in pairs in the ground state. The pi orbital, the pi bonding orbital, what's schematized here, is the lowest in energy. The N is also a bonding orbital, and that's the second lowest in energy. And then the pi star is a so-called anti-bonding orbital, and that is the lowest energy excited state. So what electronic transitions do is they promote an electron from one of these two occupied orbitals to the pi star orbital. When that happens, of course, for light to be absorbed, the dipole moment of the molecule must increase. We went through that in detail before. And so there must be a non-zero transition dipole moment, meaning difference in the electric dipole moment of the molecule, with one electron in the pi star orbital compared to the ground configuration having them paired in the pi and N orbitals. Okay, so the critical thing about CD, where CD comes from fundamentally, is explained here. I don't expect you to know anything about this. I'll just go through it very quickly. This is showing the basic quantum mechanics, a very crude way. It's showing the quantum mechanics of circular dichroism. These are actually accurate quantum mechanical equations. I'm not going to explain them in detail. We haven't gone through enough background for most of you to understand what these things are. This is something called a magnetic, effectively this is a magnetic dipole moment. Well, this one is a combination of the magnetic and electric transition dipole moments. In any event, the details here are not particularly important. I'm going to summarize the qualitative stuff. Again, I'm not going to test you on this, but just FYI. The physics of electrostatic charge in electric fields is basically achiral. The simplest way to think about that is by considering what happens if you take a positive charge and you make it a negative charge. The force goes in exactly the opposite direction, right? Whatever direction the force was on the positive charge, it will, whatever the charge interactions are, whatever the electric field is, if you change from positive to negative charge, the force goes in exactly the opposite direction. A vector in exactly the opposite direction is the mirror image of the vector that you started with, and therefore that is achiral. Electric field effects are fundamentally achiral. Now, magnetism, on the other hand, involves circulating electrons, and so then that all of a sudden you have a direction of circulation, a handedness. Magnetic fields are effectively chiral. To get, just in terms of symmetry and really sort of baseline physics, to get a molecule to interact differently with right and left circularly polarized light, effectively its magnetic moment has to change during the transition, right? Electric effects can't really, are sort of, again, fundamentally achiral. Well, the electric field, its interaction with molecules is fundamentally achiral. So electric work done on a molecule by electric field cannot have a chiral character, cannot be affected by chirality because electric effects are achiral. On the other hand, magnetic fields have a chirality. And when you can only see a difference in the absorption of right and left circularly polarized light, if somehow that will affect the probability, if something about the molecule will affect the probability of absorbance of the light of different chirality, and the only thing in the molecule that can do that, the only thing in the molecule that can do that and that can interact with light is the magnetic moment. Right, so a magnetic field, magnetic moment has a chirality associated with it. So to simplify this a little bit, but this is sort of fundamentally accurate, for a molecule to interact differently with right and left circularly for an electronic transition to absorb right and left circularly polarized light differently, there must be a change in the magnetic dipole moment, because that is the only thing that really can, the only chiral interaction with a electromagnetic field. So this is an attempt to sort of schematize this. This is showing I'm not even going to try to go through the details of this because time is sort of tight, but the idea is it's showing that a helical displacement of charge effectively is going to give you some kind of a change in magnetic dipole moment. And this is supposed to sort of schematize in a way why helical things or chiral things have circular dichroism. So again, I don't really expect you to remember any of that, although hopefully it's interesting to you and useful for you to know. What I would like you to know is that the fundamental phenomenon that sort of drives CD spectroscopy is something called coupling or perturbations of electronic energy levels. And what this is all about is if you consider, for instance, two N bonding orbitals. And so, I'm sorry, if we consider now two amide bonds, so each one has an N and an N bonding and a pi star anti-bonding orbital. They would also have pi bonding orbitals. I'm not showing that here. But the effects of those would be the same. I'm just simplifying this to get at the fundamental interactions. So I'm showing you the N in pi star bonding and anti-bonding orbitals for one amide bond and for a second. When these things come close together in physical space, they interact energetically. Why? Well, because, of course, if this is a transition that can be driven by light, and by the electric field of light, which it can, there has to be a change in the dipole moment, in the electric dipole moment of the amide bond when you undergo the transition and promote the electron to the higher energy state, right? So we do know that this transition will absorb light in the molecule, and therefore necessarily there has to be a change in the dipole moment, the electric dipole moment. Well, if the electric dipole moment changes of one amide bond and it's close to another amide bond, there will be dipole-dipole interactions between them. If they're close enough, their dipoles will interact energetically. And if the dipole changes when the electron is promoted in one, that will change the interaction with the other. And so this is sort of a pretty fundamental principle in molecular physics. It's not even really entirely quantum mechanical. It does come simply from electrostatic interactions of dipoles, and anything that absorbs has a dipole. That changes during the absorption. So what this means is that depending on the occupancy state of the orbitals in one amide bond, it perturbs the energy level of the orbitals in the other amide bond that's nearby. And so what you go with is in two isolated amide bonds, the two n orbitals would have the same energy. These are, the occupied ones in the ground state. And what this does, when you put them together, you get two different orbitals that have different energies depending on the electric dipole interactions between them. And there are some mathematical details there that are a little bit hard to explain on the fly, but I hope you get the idea. When these things come close enough together for their dipoles to interact, they split. And what would be an equal energy level here now splits into two different energy levels. The same thing happens in the pi star antibonding orbital. The equal energy levels in the separated molecules now split in energy level depending on the electric dipole interactions with the nearby amide group. And so to oversimplify this slightly, basically if you have an unfavorable, if the nearby, this pi star orbital in one amide bond will have a different energy level depending on whether the nearby amide bond is in the n or the pi star state, because there's a different electron dipole moment in the n versus pi star state, and one will be higher than the other, and therefore that'll cause a splitting in these energy levels. So basically, this is again called coupling or perturbing or delocalization of electronic energy levels. And when you bring two amide bonds together, you get a doubling in this way. When you bring a large array of amide bonds together in a polypeptide, or a large array of nucleotide bases together in a DNA or RNA polymer. In those cases, you're looking at different orbitals, but it's the same principle. This transition dipole moment coupling or perturbation produces delocalization of the orbitals. And when the orbitals are delocalized, their energy level shifts. And this is really what CD is all about. CD is looking at, in a clever way, the perturbation in these energy levels by the through-space interaction of the dipole moments, and particularly the transition dipole moments, because it's looking at the difference in the dipole interaction energy from ground to excited state. And so this phenomenon is called transition dipole moment coupling. I don't expect you to know all these details, but I want you to know is that energetic dipolar, particularly electric dipole interactions between the amide bonds close together in space, couples the energy levels together, splits them apart, and when that splitting occurs, guess what? The electronic absorption spectrum changes because the ground state energies shift around and the excited state energies shift around, and now the difference between them are transition energies. The transition energies correspond to the absorbance wavelengths. When that happens, the frequency of the absorbance, wavelength of the absorbance, and the amplitudes of the absorbance change. The amplitudes change because the transition dipole moment magnitudes change when you're going between delocalized states compared to the simple isolated electronic states. So what do I expect you to memorize? Remember here two things. Transition dipole moment coupling. This phenomenon requires coupling of the transition basically the transition dipole moments between amide bonds close in space that produces delocalized, effectively orbitals, electronic states, and they have different absorbance properties. So that's number one. Now, you could try to quantify secondary structure this way, but that would be numerically very unstable. It turns out that when this kind of coupling happens, you now have a rather strong perturbation of the magnetic dipole moments. And that's sort of what they're attempting to show here. In an alpha helix, you're going to have all these amide bonds coupled together in a helical pattern. They're trying to schematize here the idea that that helical pattern allows you to have sort of a spin of the electron. I'm not convinced the physics here is absolutely rigorously correct, but I think it's giving you the idea that when you have a helical arrangement of delocalized electronic orbitals, it's going to have the capability of having sort of more differences in the spin characteristics. And the spin characteristics...
It's 7:30.
The spin characteristics are what gives you circular dichroism, differential absorbance with right versus left circularly polarized light. This is based on something called the magnetic transition dipole moment. I won't go into it in detail, but you can just imagine from the name that it's working in a similar way to the electronic transition dipole moment, but it's chiral. And when you get these delocalized modes, they are now strongly chiral, right? This helix is very chiral. It is right-handed. The electronic states are now chiral. The chiral electronic states now will interact differently with right and left turns of the circularly polarized light, and you get these basically chirality fingerprints, and that's what circular dichroism is. Okay. And so what you get then is you get differences in sign. In some regions, you get more absorbance of the right circularly polarized lights, in others of the left. And the way that those things switch around depends on the secondary structure content, because the secondary structure changes the chiral nature, effectively, of the delocalized electronic orbitals. Again, what do I want you to remember here? I want you to remember that this transition dipole moment coupling, sorry, slightly geeky there, but I think I can get this. Transition dipole moment coupling produces delocalized molecular orbitals, point 1. Those have a chiral character that now enables you to see circular dichroism, point 2. This is just showing the same thing. I'm not even going to go through it in detail. This is just blowing it up. If we had more time to go through this, I'd talk a little bit about this. This is just breaking down the specific electronic transitions you're seeing in different regions of the spectrum. Where we are now in this point in this course this year, given the chaos we've had for the last week, I don't think that this is irrelevant. So it's FYI for the moment. I think everything relevant was covered in the preceding slide. Now, what is this mess? You can ignore the vast majority of this. This is here because in case you ever need to do CD yourself, this tells you the foo to do it properly. As I told you at the outset of this mini lecture, the authors of that CD website did not, which is supposed to be instructional, did not properly normalize their spectra. They didn't do it because it's a bit of a pain in the ass, but to make it easier for you, I've put all the numerical calculations that you need to do this properly right here on this slide. For the moment, they're unimportant, except for you to know that they are here. So that's, I guess, point 1. Point 1, I want you to know that this material here tells you exactly what you need to do CD properly, should you ever have the great fortune or misfortune. Sorry, that's a bit of a mess, but this tablet's a bit hard. Okay, this is, the magic handshake is here in case you ever need it. The other thing I want you to know is that the units are bizarre. Basically, CD follows the Beer-Lambert law. I'm sure you've all heard about that in terms of just regular electronic or optical absorbance. The absorbance is typically epsilon CL, extinction coefficient, concentration, path length. Here is sort of a delta absorbance because it's the difference in absorbance to the right. So this is effectively a delta epsilon. And I don't care about the math here. But so this is the Beer-Lambert law extended to CD. But when CD spectra are published, it is quantified in terms of, path length is quantified in terms of centimeter, sensible, concentration in terms of decimole per mil, which is totally bizarre. So the units of CL in this Beer-Lambert law for CD are decimals per mil. And I don't even care if you remember what the hell that is, but just I want you to remember it's bizarre. There's no good reason for it. It's a convention that should have been killed off, but is not, and I doubt now at this point will be anytime soon. So if you publish CD data, you'll have to know it. Okay, so this is supposed to be mean theta. Theta is ellipticity. I'll talk about that in a moment. The mean residue ellipticity is the ellipticity per decimal of amino acid residue per milliliter of volume per cm of path. You have to put your data in this weird format to put in analysis programs, including the analysis program written by the group that put the website online that didn't have the data properly normalized. So again, this point 1, this mess up here tells you how to properly, oops, I'm sorry. The mess up here tells you to properly normalize your data, and you need to, into mean residue to see what you need to do to analyze it. And then there's some other instructions are provided down here. Now, the only other thing I want you to know here is that ellipticity is measured, CD is measured in ellipticity. What ellipticity is, I don't care if you remember the mathematical details here, but I want you, CD is measuring the difference in absorption of left versus right, but it's measured in ellipticity. Where the hell does that come from? Well, ellipticity comes from what happens, as I said a few slides ago, if you have an equal amount of left and right circularly polarized light, you get linear polarized light. As the amount of left and right circularly polarized light becomes unequal, you get an elliptical path. Theta, the ellipticity, is measuring sort of what's it measuring? How it's measuring effectively. It is a measure of the difference in the magnitude of the electric of the right-handed and left-handed contributions to the I'm sorry, it's measuring the difference in the left and right-handed circular polarized components contributing to the total intensity of the light. And I guess the only thing I want you to know here is that this is like a weird measure. But I guess the other thing I want you to know is that typical experimental ellipticities are 40 milligrees, or 0.001 radians. These are small angles, and so tan theta is basically about theta. And so what this means is the difference in the transmitted intensity of left versus, if you do all the math here, and I don't expect you to do that, the difference in the transmission, this is a strong CD signal, is 40 milligrees, corresponds to a 0.4% difference in absorbance between right and left circularly polarized light. So this I want you to remember. To measure CD involves measuring really small differences using a weird angular convention. And so so think about it, 40 millidegrees would be, this would be like, whatever, 30 degrees. 40 millidegrees would be some tiny, 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 tiny angle. And the reason for that, if you think about it, and I don't expect you to do this today, but it's because there's a very small difference in the absorption of right and left circularly polarized light, and that makes this angle very small. So that's all. So the circled things are all I really want you to know about here. This is just showing an instrument. I don't really want or expect you to know much here except for one thing. So because the differences in absorption of right and left circularly polarized light are small, if you have samples that don't absorb much light, it's hard to quantify a small difference of a small amount. So you want a large absorbance. And so you try to get a CD measurement where you have a lot of light absorbed. Of course, if too much light is absorbed, none comes through. The sample is opaque, and now you have a big, well, basically, if you don't have a large absorbance, the signal is too small to measure. If you have too large an absorbance, the sample is just opaque, and even there's a significant difference between them. You have no photons coming through, and you can't measure a difference where you can't count photons. And so most CD machines, again, use a weird measure. This is sort of indirectly related to absorbance, but every CD machine I've ever worked with has the same convention because I think they're using the same photomultiplier. They measure a dynode voltage. The dynode voltage is basically what they're doing, how they're amplifying the photon signal. And so if there are too few photons, you have to amplify it more. The dynode voltage goes up. Every instrument I've worked with, if the dynode voltage goes above 500, it means the signal is opaque. And the way these things are designed, unfortunately, they will give you CD signals and they will be spurious. So you have to know to look at this dynode voltage. If it's above 500, the sample is opaque and you're measuring nonsense. I have seen people do this in published papers, unfortunately. But I'm warning you against this pitfall. So that's really the only thing I want you to remember here. And then this is making the point, sorry about that. This is making the point that pure secondary structures have distinct CD shapes of their CD signals and distinct magnitudes. The biggest one here is the alpha helix. It is the biggest in magnitude, and these accurately reflect the relative magnitudes of the signals coming from different secondary structures. So I would like you to remember that this characteristic double minimum, 208, 222, and approximate 197 is characteristic of the alpha helix. That you have to get the absolute magnitude of this correct to really do the fitting of the secondary structure content. And they haven't done it here yet again. For the same website I showed you before, incredibly enough, these people are CD experts and they have not put the data in the right format. Random coil, I'd like you to know, has a very deep minimum at about 198. And so that's another distinct thing that's pretty easy to measure. Beta sheet actually does not have much of a signal. It has a minimum of 217, but not but only a weak one compared to the alpha helix. It has a peak then at around the same position, but different magnitude. This is effectively why it's so important to get the absolute magnitude correct, because that's a big way that you tell how much beta sheet you have in the end. Beta turns, if you know what those are, this is sort of cool. If you don't, ignore it. They have a very strong CD signal. It's very distinctive. But this would be like a mole of beta turn, and proteins at maximum are like 1% beta turn. So this is sort of cool in principle. It's useless in practice. Okay, but the things I want you to remember here are the circled things, the double minima for the alpha helix, the deep single minimum for the random coil, and the fact that the absolute magnitude on the proper scale at about 197 must be measured accurately to do secondary structure decomposition. I guess one other thing I would like you to remember here is what's this point here. The fitting procedures are not robust because the chi-square function has a shallow minimum, and that makes curve fitting sensitive to noise or inaccuracy, even with good basis spectra. Basis spectra are inaccurate for irregular conformations and sort secondary structural elements, an additional complication. So so you got to be careful when you do CD, and again, it's a semi-quantitative estimation of secondary structure content. In practice, the chi-Ferris function is so shallow, no one really fits these data anymore using a chi-Ferris square function. Fancier numerical techniques are used that do a bit better, but still don't do well, and really likely to completely screw up unless you've measured the 197 peak and have it on the right absolute scale. Okay, so that brings us back to these points. I won't repeat them, but they are important. And sorry, this is coming you at the last minute, but I will. But this stuff is worth knowing if you're going to go on in biochemistry, molecular biology, or biophysics. And I'm sorry it's coming through to you sort of late in the game.